It's possible. I'm not sure. Yeah. Let's see if people can hear me. Yeah. Hello, can people on Zoom hear me? Best. All right. Good afternoon. How's everyone doing? All right. Let's see. Last week before spring break. Ready? Happy St. Patrick's. See, a lot of people are wearing green. I think these jeans count as greenish. All right. Let's see. We still have some assignments due before the spring break starts. We've got Lab 8 and Project 2B that are going to be due on Friday. So get working on those. All right. One last thing for those of you on Zoom chat. I think Josh is busy today. So I'm going to try to answer Zoom questions whenever we are answering questions. But just be aware that there might be some time delay between when you ask a question and when you get it answered on Zoom. All right. So last time, we kind of introduced the concept of the graph class. The idea is you have some nodes, and then you have connections between these nodes. And these can be either directed or undirected, depending on the type of graph you're dealing with. So our first question for today is going to be how we actually represent that within code. And the way we represent things in code are going to end up affecting the difficulty we will have when we solve problems using it. Ultimately, we're going to be creating what we call an API, the application programming interface. It's kind of the same thing as the interface that you might have with a list class or with the tree class. In effect, we're just trying to create a standardized system by which all graphs can be used. Now, our first simplification is that we're going to kind of restrict our graphs to this kind of simplified version. We'll have, instead of labels assigned to each node, we'll just have numbers assigned to each node. So each node will be a number from 0 up to the number of nodes minus 1. Uh, in reality, we can kind of use this in the same way as any graph that we want, which has labels that are a different type. We just use a map in between. And we've shown that using maps, you can get constant time accesses in both directions. Here is kind of the simplified graph API that we'll be using for this class. So we'll start off by just creating a new graph. And the new graph takes in as input a number of nodes. So they'll create an empty graph with exactly V number of vertices, kind of similar to how a weighted quick union does things, right? When a weighted quick union, you ask it to create a weighted quick union with V nodes, and you get a bunch of nodes that are entirely disconnected at the start. We also have the add edge operation, which adds an edge between two nodes. These are simple graphs, so we can't have like two edges connected to the same two nodes. I think it'll just override one of them. And you can't have self loops, like a loop that connects node 1 back to node 1. That's not allowed. Uh, and it also doesn't support adding weights to edges. We will talk about graphs with weights on edges later. But for now, we can assume that these are just graphs with nodes that have numbers 0 through n, and which have edges between them that have no weights whatsoever. They're just connections between two nodes. They're not like, they don't have any values associated with them. We also want an iterable over all the adjacent nodes. So if you're at a node, you should be able to tell all of your surroundings. And then other than that, we have some size operations, the number of vertices, the number of edges. Those are just kind of auxiliary. They help make things run, kind of like size methods in lists. Now, this structure, it needs the number of vertices to specified in advance. You don't have weights, and you kind of don't have a way to get the degree of the vertex. If you do want to make a function that gets the degree of the vertex, how might you do this with this code? Yeah.
Counter to the add edge operation.
Huh?
Will you add a counter to the add edge operation? So every time you add an
You can add a counter to the add edge operation. Yeah, if you wanted to, you could have like a number associated with each node that just counts up each time an edge is added for either B or W, and then return that. If you didn't want to kind of memorize it, like store that value within the code, how would you do that? Like imagine that you had this graph class, you only were able to access graph operations using that, and you kind of built a method on top, or maybe like an interface default method. Yeah. Huh? Yeah, you can iterate through adjacent and count out the total number of items in the adjacent. Here's kind of a quick example function for this. You start with 0 as the degree, and then for each node in the adjacencies, you just increment the degree by 1. So let's do a quick example. Let's try to come up with a program that'll print out all of the edges in a graph, one at a time. And feel free to discuss with your neighbors. I'm going to take this time to look through Zoom chat, see if there's anything I missed. Let's take 2 or 3 minutes to come up with an algorithm for this. Do iterables have a size method? That's an interesting question. Let me take a look. One of the useful things about the Java libraries is that you can kind of like look them up. So if I go into Java's iterable class, Size. It does not appear to have a size method, the iterable class. Let's check the iterator class. Does an iterator have a size? Nope, does not seem to have a size method. And in some ways, it kind of makes sense because not every iterable is or iterator is going to be finite sized, right? You can imagine that you had those Python generators that created an infinite number of items. You can kind of do the same thing with an iterable. So you don't necessarily have a size. Are we printing out the vertexes or the edges? We are printing out the edges. Yes, good point. And we are specifically printing out each edge twice uh, in this kind of format. Although if you have the chance, you can kind of think of how you might also set it up so you only print each edge once. There are solutions for both. All right. Let's bring everyone back. Yeah, let's bring everyone back now. So, how'd things go? Did anyone come up with an idea on how you might print out all the edges in a graph? Yeah.
You can recursively call the string method on like all in these times to vertex line and only kind of like recurse through all the edges even off like there's two links like one link for item chain, one link back to
You could recursively call it like print out all the adjacencies and then keep going. That would work if you're careful, right? You don't want to accidentally get stuck in an infinite loop, kind of like how we did with the depth first search. But you could probably work that out. One of the issues I would see is that this doesn't work if the graph is disconnected. Like you can imagine that you have two components that are entirely not connected to each other. If you run it on just one of the components, you're never going to get the edges on the second. Yeah.
0 to v-1 and then have a nested for each loop that goes over whatever vertex you're on or ADG or ADJ of whatever index you're on. And then inside of it have to go to just the print your current vertex space dash.
Mm-hmm. Yeah. In effect, you can kind of just iterate from node 0 up to node 3, look at all of each node's adjacencies, and then just print out one edge for each one. Now, how might you set things up so that each edge is only printed one time? You notice here that every edge is printed twice, once 0, 1, once 1, 0. Does anyone have any ideas on how they might prevent that from happening? I'm going to try to pick someone else. Sorry. Yeah, you have? Yeah, yeah, you can kind of just do if the adjacent node is bigger or if the adjacent node is less. Since each node is a different value than its adjacency, that'll ensure that each node appears or each edge happens exactly once. Now, depending on how we define our graph itself, these operations like print or degree might have different runtimes. So the actual concrete implementation of how we build the graph, it's not going to affect the API. It's not going to affect how we use the object, but it is going to affect how much time it takes to run things. Kind of like how an electric car, it doesn't affect how you drive the car, but it is going to affect the amount of pollution you produce or the number of times you need to go to a charging/gas station, that kind of thing. So one common design in these graph algorithms is that you kind of split things up into two sections. You have a graph class that is kind of this bare bones noses and edges representation. And then you have a wrapper class around that that does the operations you're interested in. There's a lot of different questions you can ask about a graph. So it makes sense to have a standardized graph class first, And then from there, have specialized classes that ask different questions about the graph. You remember the weighted quick union class, which just had the problem of, is there exist a path from one node to another? You can imagine that you can do something similar with a graph class, and then just have an is connected operation in a separate, like, higher level class. The only reason why we don't do that is because for this particular question, the weighted quick union question, it's much faster to use your own personalized version of the class. You have faster runtimes if you manage to not care about the graph itself and focus on, like, connecting components. The main difference in this class is that we also have this path to operation, which asks you not just is there a path, but to tell me the path that goes through. So you're unable to just simply connect things in that tree structure because now you need to know how to get from point A to point B. So you might imagine that this is the structure of how you use this paths object. So you create some graph somehow, let's say this graph here, and then from 0 up to 3, you call it and it returns the path from 0 up to 3. In this case, 0, 1, 4, 3. Now, let's take a look at the depth first paths that we kind of ran last time. So here's kind of the quick algorithm for how this works. When we were checking to see if two nodes are connected, we came up with this algorithm last time. And in fact, what we do is we start off at a node. We check if S is equal to the target node. If it is, we're done. We've found a path. Otherwise, we go to every unmarked vertex neighbor and just call connected on each one. And if any of them return true, then we have found a path and we have successfully managed to find that there exists some path. It might not be the best path, but at the very least, it is some path, and we know that it is connected. So let's kind of walk through this. If we're trying to see if 0 and 7 are connected, first thing we do is we check, is 0 equal to 7? Is 0 the same thing as 7? No. So because of that, we'll mark 0, and then we'll look at all of its connected neighbors to see if any of them are connected. So what do we look at next? 1? Yeah. So we go to 1, and we look, is 1 the same thing as 7? No. So what do we go to next? Well, first we mark 1, and then we'll look at one of its neighbors. In this case, I'm going to pick always the smaller number to look at first. So I'll look at 2. Is 2 equal to 7? No. So what do you look at next? 5? Yeah. So now we check 5. Is 5 equal to 7? No. What do we look at next? 4. Is 4 equal to 7? No. What do we look at? 3. Is 3 equal to 7? No. What do we look at here? Good question, right? We don't have any more edges connected. So this is the point where the recursive call starts coming back a bit. So the 3 is going to return false because it couldn't find anything. 4 looks around. It doesn't have any other neighbors that are not connected. So it's going to return false back here. 5, does it still have unconnected neighbors? Yeah, so now look at 6. Is 6 equal to 7? No. So what it'll do next? Yeah, it'll go up to 7. Is 7 equal to 7? Yes. So now that it's found the 7, it'll go back down and return the true up this recursive call stack, eventually making its way back to the start. And everything is true at the very end, connected returns true. Here's kind of the overall structure and how you might solve this problem. You create this depth first path constructor, which just runs this DFS operation. And the idea is, instead of just computing the path from like one node to another, we're going to compute all the paths from 0 to every other node. Since it seems like we're doing this already, we're finding a lot of paths. We're determining if things are connected to 0 a lot just in this operation. So that's kind of the reason why we're setting up this paths class at the start. We're going to create this map showing how to get from each node up to node 0, all in the constructor. So that way, when we query things later, it's fast. So as an example here, this path that we found when we checked connectedness, we were able to find the path to 7 that goes 0 to 1 to 2 to 5 to 6 to 7. Internally, what do you kind of need to store in order to express that? What's the minimum amount of information you need to store to express that if you wanted like a path from 0 to every other node? Not any vertex to 0 specifically. Yeah. And it doesn't have to be the best path. It just has to be any path that goes there. Yeah.
You could store some set of all elements that are connected to 0, and then whenever you're checking for a new element, if it's connected to any one of those elements, you can instantly say, well, therefore it's connected to 0.
Okay. You could create a list of all the things connected to 0.
Like a set.
Yeah. And then look, is anything connected to one of those?
Yeah, or
But that only reduces the time cost by 1, right?
I mean, you could also just rush through the. Actually, never mind.
You could traverse through everything, but that takes too much time. I want to set things up so that I create one thing first, and then from then on, I don't need to further do any math. Do you have an idea? Yeah. Mhm. Yeah, you can kind of imagine that 7 just needs to know how to get to 6. And then from there, 6 knows how to get to 0 because you're storing a path from every node to 0. So you can imagine that 7's rule is go to 6 and then just follow 6's path. 6's rule is go to 5 and then follow 5's path. 8's rule is go to 5 first and then follow 5's path to 0. And so on and so forth. You kind of create like a subtree of this, a set of edges that form a tree within this graph. And then you're just saying the path to 0 from there. Yeah. Well, you store if there are two paths. Well, this class doesn't actually need to know that there are two paths. We can just pick one of these randomly and decide to say that. So for example, 4, it has paths 1, 0, and it has 5, 2, 1, 0. In this case here, the way that we set up the recursive call structure, it'll probably say that the path is go to 5 first, and then go from 5 to 0. Yeah. So good question there. You don't need to have the best path in this case yet. We just want any path. So we might just say to get from 4 to 0, go to 5 first, and then follow the instructions from 5 to 0. Yeah. We could have easily said take the instructions from 1 to 0 first. Yeah. Yeah. We'll internally formalize this as this edge 2 graph. In effect, each node knows how to get to the next node on its path to 0, and that's it. And then we kind of just keep following those nodes, kind of similar to how when we had this weighted quick union, right? We had each node know its immediate parent, and then you can follow the list of parents all the way up to the root. Same thing here, we're using 0 to define the root of this. Now, how we rewrite a path to operation? Well, we kind of talked about this in a way. If we didn't have a hash path, then we can just return null. And if we wanted the path specifically, then we just kind of go up this chain and kind of inserting it into some iterable object over and over. Now, we do have to be careful at the very end. We should reverse the path because we've created a path from 7 to 0, and this class wanted a path from 0 to 7. But otherwise, it's the same thing. Yeah.
Data structure or data for finding the path from 0 to all of them.
What data structure do you want to use to store this data? Good question. Well, all we really need is an iterable. What type of iterable do you think is going to be most appropriate here? A list of some kind? Yeah, I would say a list probably because you want like a sequence of things in a particular order. Other operations for other options for iterable, like sets, they don't have an order, so you don't really have a way to say, like, to go from 0 to 7, you take 0, 1, 2, 4, 7, right? Or 4, 6, 7. With the list, you can kind of say to go from 0 to 7, you go 0, 1, 2, 4, 6, 7 in that kind of order. That makes sense, or are you still? Yeah, so within the depth first pass object itself, you do want to have all those paths available. And we kind of store that in, or encode that within our edge2 array. But each time we query this particular data structure, each time we ask one bit of information, we're asking specifically what is the path from 0 to a particular target node. So while we need to know the path from 0 to 1, 0 to 2, etc., we only ever ask for a path from 0 to 7 or a path from 0 to 3 at any given point. So our return value in that case would be just a single path. Yeah. So let's kind of figure out how we can make our graph class internally so that it is efficient to do this. Now, our main constraints here are going to be the runtime and the memory use, because those are going to be affected depending on how we define our graph. The difficulty of implementing the graph algorithms, that's actually not going to be affected too much because we've standardized the graph class API itself, and we're building these graph algorithms off that graph API. We've kind of split things up between building the graph and building the graph algorithms effectively here. So let's kind of go through an analogy, right? Remember when we discussed trees, we had a lot of different ways to build things, right? What types of trees did we talk about in this class? Binary search trees, left-leaning red-black trees, 2-3 trees. We also saw these weird like heap type trees where you had a number of links or you had this structure here. All of these are different valid ways of using a tree. But if you're using a binary search tree, you'll have a different runtimes as an LLRB, for example. We also saw that with project 1, right? We had lists or decks, which had different runtimes depending on how we did things. How fast was the linked list operations if we had to like get an item in a linked list? O of n, yeah, linear time. How fast was the array list? O of 1 amortized, yeah. Yeah. Amortized meaning that not every operation would be fast, but it'll be fast on average. Mm-hmm. So we could see that depending on how we define the internal graph class, we're going to have different runtimes. So how would you represent things internally within a graph? Like how would you kind of represent a bunch of nodes and a set of edges that go between these nodes? What do you think are good versions? Talk with your neighbor. Let's come up with, let's take a few minutes on this. I will say that there are multiple different possible ways to do this and multiple different ones that are actually used. So you might come up with different ones from your neighbors. Feel free to discuss. Let me see if there's any questions on Zoom.
Yeah, just do this.
Oh, yeah. Yeah.
All right. Let's bring everyone back. Just in the interest of time, let's bring everyone back. So what did everyone come up with? What ideas do you have of actually representing a graph in memory? Uh, yeah.
Uh, a graph class that has node type class that points to multiple other nodes.
Okay. So you have a node, and it has internally a list of adjacencies. And each node within that, or the list of adjacencies is kind of the list of all nodes that are connected. Yeah, that seems reasonable. In order to add an edge, what would you do?
Add to the list of adjacent.
Yeah, you look at, if you're connecting U and V together, you look at U, add V to its list. You look at V, add U to its list. That seems good. Any other approaches?
You can have a 2D array or a hash map where the values are arrays, where just like the key or the index of the row will just be your node, and then the subarrays are just the children. Or you can have a 2D Boolean array where I, comma j just tells you whether I'm.
I could create a 2D Boolean array, like an n by n. How would you connect U and V together?
U and V together. You would just set U comma V to true and V comma U to true.
Yeah, if you have everything initially set to false, to connect U and V, you just set U comma V to true and V comma U to true. You also mentioned a hash map version.
Yeah, where the keys are just all of your, so if you have like 5 nodes, your keys are just 0, 1, 2, 3, 4, and then the value of every element in the hash map is just some array list with the numbers of the.
Yeah, that sounds similar to the like node with list method that we had. Was there any other approach? There's, I think, one other that I cover here. Yeah.
You do a map where you have the values, like you have the key and then the item is a list of other keys that it's connected to.
Yeah, you can kind of do a map from key to other items. That I feel is kind of also similar to the adjacency list idea. Yeah, I think that's the fact that three different people came up with the same idea shows kind of his foreshadowing a bit. Yeah. So ultimately, this is kind of the first approach you might use. You have this adjacency matrix where you just have an n by n matrix. How do people feel about this? Do you think this is fast to use? No?
Fast lookup.
Fast lookup, we can check to see if two things are directly connected. It might take a while to find all of the adjacencies of something. Is it memory efficient? No, this array is really, really big. It's n squared memory when you have n nodes. So this generally doesn't get used too often unless you have really, really bushy graphs, where if there's a graph that has a lot of different edges, like close to n squared edges, then this might be useful because most of the edges exist anyway. Here's another approach that I don't think anyone mentioned. The idea is you just create a set of all the edges that exist within the graph. So this graph is represented by 0, 1, 0, 2, and 1, 2, all the edges. How do people feel about this? Is this efficient? Well, it seems efficient to find if a particular edge is in the graph, right? Sets can be constant time access. You can check if two things are in there. It might take a while to look through all of the edges to find the edges that are connected to 0. So adjacency might be a bit slow. Yeah.
If you were like actually implementing this, would you like create like a custom tuple class, or if you have like where 1 comma 2 has the same hash as like 2 comma 1? Just so you don't have to store as any like if you have an edge between 1 and 2, you don't also have to store the edge between 2 and 1.
Good question. If I were to create this, would I create a custom edge class so that, for example, 0, comma 1 is equal to 1, comma 0? I might. Yeah. Another approach would be just be to use a standard equals class and just always store things with small or greater, right? Kind of like the print version that we discussed, right? You can kind of do the same thing here. Mhm. Yeah, the third approach is the one that a lot of people came up with. And the idea is you just create an array of lists, each one associated with one vertex, and each one containing all of the adjacents. So 0 is connected to 1 and 2. So we have 1 and 2 in this list here. 1 is connected to 2, so we have this here. 2 doesn't have any connections going out of it, so we have no items in its list. How do you add a node to this, or how do you add an edge here? Add to the lists. How do you go through an iterable of all particular node's adjacencies? Yeah, iterate through the corresponding vertexes items. Yeah.
In a directed graph, the arrow, can you have the arrow point for both ways, or does it only have to point one way?
In a directed graph, can you have the arrow point both ways? Yes, generally speaking, when we're dealing with directed graphs, I would allow both an edge from 0 to 1 and an edge from 1 to 0 to exist. Now, depending on who's writing it, you might have bidirectional arrows, or you might have two separate arrows pointing one to the other. But they're effectively the same thing. I would consider both of them to be simple directed graphs, even though there's kind of like two edges associated with it. Although, depending on who you're talking about, it might be different. Yeah.
That you're not all graphs are connected. If you look connected, you can basically the roots instead of this, and then
Yeah, we can't necessarily specify a root here because graphs don't have a concept of a root necessarily. You are correct that sometimes graphs may not be connected, but it also is true that there might not be a canonical root within the graph, right? For example, if this edge was going from 2 to 1 instead, sorry, that's the wrong one, from 2 to 0 instead of 0 to 2, you can imagine that you just have like three nodes that are all connected to each other. There's no real one that counts as the root or like the core starting point here, right? Like you can imagine a rock, paper, scissors graph. Rock goes to paper, or rock goes to scissors, which goes to paper, which goes to rock. There's no root. There's no best operation here. Yeah.
or like word type is kind of like different arrays, you can't really add word types.
Yeah, you can't add new vertices, but we already specified in our graph API that that's not something we care about. We only want to start off with a fixed number of vertices. Yeah. You may be able to add more vertices kind of using a resizing array, right? We've talked about how resizing arrays can run quickly. You just kind of replace this with a list instead of an array. But in this particular case, we don't want to add new vertices. Yeah. So the adjacency list is going to be kind of our go-to for most cases. You might prefer different ones, especially in Project 2B. So what do you think is the runtime for this adjacency list code? Let's take a minute to discuss. The yellow key doesn't work, by the way. Please don't use it.
You have to do a very
All right. In the interest of time, let me bring everyone back. I know the discussion just started to get really interesting, but how many people said it is theta of v? How about theta of v plus e? Few people. Theta of v squared? How about v times e? Few people as well. It's kind of tricky here. Let's kind of think about how you might solve this, right? First off, how many vertices do we have? V of them. So this for loop is going to iterate V times. For each of these vertices, we're going to go through this code. How many adjacencies do each node have? Yeah?
They can have, each one can have up to E.
Each one can have up to E. Well, that is a bound, yes. You can have at most E edges. Are there any other bounds you might have? Yeah? Up to V, yeah. We don't know whether V or E is going to be bigger, so we will probably want to describe both of them. Uh, yeah, but yeah, you for any given node, you can only be connected to up to V minus one other nodes because you can't connect to yourself or you can't have multiple edges connected to the same thing. Yeah, and the number of edges is a number bound on how many edges any particular node is associated with. So you can say that the best and worst case is V and V squared. But as it turns out, there's a better way to evaluate this. Kind of the reasoning here, you have to look at it a bit more carefully. But the idea is that for each edge, it contributes to one of these internal loops exactly in two cases. If you have an edge from U to V, you'll add one to the runtime of the U node, and you'll add one to the runtime of the V node. So overall, the total number of iterations that this internal for loop does is 2 times E. So we have 2 E runtimes of print. And meanwhile, this outer loop, it takes V total time just to iterate through all the items. So overall, you're going to end up getting V plus E total runtime to iterate through all of the nodes and then iterate through each of the individual edges. This is kind of a bit more tricky asymptotic analysis because you can't just go through, look at the for loop and then look at the worst case runtime within each for loop because you actually get a worse bound just by doing that kind of analysis. Yeah, do you have a no? Yeah.
Oh, in the case of E, you can only have up to like V squared minus V a number of edges, right?
Yeah, E is also bounded by V squared minus V. So when we saw our worst case was V squared, that's because in the worst case, we have E equal to theta of V squared, and V plus V squared is theta of V squared. Yeah. So I will make a point here that when E is really big, you are going to end up just back to V squared because the maximum number of edges is V squared. When E is very small, you're going to end up at theta of V. So this kind of captures both sides of this. Now we could have said theta max V comma E. Addition kind of works like the max operator in theta classes, as we saw. Both are technically correct, but I think people like the plus operation better because plus is faster to say than max comma. We also never really defined asymptotics at multiple variables. As it turns out, it is very hard to define things nicely. You can see this paper, which talks about how it is impossible to make a definition that acts nicely with all of the things we like about simple data bounds with one variable. So this is going to be kind of a more intuitive definition here. We won't be formally defining it in this class. If you want, read through this paper. It is very math heavy. Now, how much time does it take to run this code? Well, the DFS operation is kind of the main code here. We're kind of finding all of the paths. How much runtime does DFS take? What would you say? Just kind of first off the top. I would give time to discuss. I think I don't have enough time for this. Well, let's look at what's happening, right? We have an iterator through all of the nodes. How much time does this take? V? Yeah. Uh, so, sorry, I'm doing this wrong. In order to run this, DFS is going to be called on each vertex at most one time each, right? So we'll have at most V distinct calls to DFS. Within each one of these calls, we'll go through this for loop. What is the total number of steps that this for loop is going to be running if we run this over every single possible vertex? E, yeah, because each time we have an edge, it's going to contribute at most twice, once to the DFS call for U, once to the DFS call for V. Overall, what's our total runtime? V plus E. Yep. Now, this isn't theta of V plus E. It is O of V plus E. Why is that? Are you raising your hand in the back? Nope. Yeah.
Because there might be an isolated vertex.
Yeah, there might be isolated vertices. You might start at an isolated vertex. So in practice, this is going to be an O bound. You're not going to be able to get a precise theta bound because depending on the graph you're working with, you might have cases where you have a lot of edges, but this runs instantaneously because none of them are connected to the start. Similarly, could we say the runtime is O of E? Because like we can only ever visit a vertex if there's an edge to it. The number of edges should be bounding the number of vertices that we're working with, right? What do you say? Yeah.
Technically, if you're starting at an isolated node in a graph that has no edges, then it would be, I guess maybe that's not a good example.
Yeah, if you start with 0, then that's we do kind of ignore all the cases where the number is really small.
Yeah.
So I wouldn't count that case. Yeah. This is kind of tricky. I'm going to spoil it and say that this is not O of E. There is still some component that takes V time, even if you have very few edges. And it's not really seen here because I kind of hid it in this like dot, dot, dot section. But that's because when we actually create this, we actually have to make these arrays. And to make an array with n items in it, you actually need to take n units of time to run. These arrays have v total items in it. So you do have a theta v runtime step here.
Oh, we're counting the graph creation as well.
Yeah, this is the entire graph creation, the entire constructor here. Yeah.
But that what like isn't that like only at the beginning?
Yeah, it's only at the beginning. We're talking about the constructor runtime. We're not talking about the runtime of like the individual queries. Once we build this, the queries are really fast, but the constructor is going to take a while to run. Yeah. So overall, we are going to get O of V plus E, and the space we need is theta of V. Now, there's one last part that I want to cover here, and that's kind of like the another way to come up with paths. Here we had just any path, but now I want to go for the shortest path in each case. Now, if you're on the video, please take a step here to just kind of think about this. For the interest of time, I'll move ahead. But this is a good point to kind of try and figure out if there's any algorithm to come up with this. I'm going to spoil the way to do this now. All right. So in a way, one way we can do this is by this breadth first approach. Instead of just going an arbitrary path, because that might yield, for example, 0, 1, 4, 3, 2, 5, 6 is the fastest path to 6. That's not true. If we want to make a shortest path, what we'll do is we'll kind of go one layer at a time. So we'll start off at node 0. And we'll look at all of the nodes that are 1 unit away. And we'll say those go directly to 0. Then we'll look at the nodes that are 2 units away. And we'll have them go to something that's 1 unit away. Then the nodes that are 3 units away, and so on. This is going to be kind of a structure that we'll see in a lot of different graph algorithms. And we'll call this Q a fringe. The idea is that our fringe is the set of nodes that we've seen, but we haven't yet done stuff with. And this is going to be kind of how we do things. I'll start off by looking at 0. 0 is our starting point. And what I'll do is I'll add to the fringe all of its adjacencies. So 0, it is the closest thing to 0. There's nothing that we connect to. So I'll add 0 to the fringe, and then I'll just take it off immediately. For this, when I take something off the fringe, I'll just look at all of its adjacencies and add that to the fringe, and I'll mark the path in this list. So in this case, the only adjacency is 1. So I'll add 1 to the fringe, and I'll say that 1, the way to get to 0 fastest is by going directly to 0. And it has a distance of 1. What now? Now I'll look at 1, and I'll look at all the things that are connected to it. What is connected to this? 2 and 4. We do look at 0, but we throw it away immediately because that's already been checked. So I'm going to add 2 and 4 to this. And for both of these, I'll say that the path to get to 0 goes through 1. To get to 0, you go to 1 first. What do we do next? I look at 2, and I add what to the fringe? 5. Yep. I take 2 out, and I connect 5. I know that 2 was distance 2 away, so now 5 must be distance 3 away and goes through 2. What do I look at next? 4. Yeah, I will look at 4 here because that's my next thing that's distance 2. And what's connected to that? 3. So I go to 4, I connect the 3. 3 is now distance 3. What do I look at next? 5. What do I look at? 6 and 8. So those go back into the queue. And because 5 is distance 3, we now have distance 4 nodes. What next? We look at 3. 3 isn't going to do anything because it has no more adjacencies, but we still need to look at it to remove it from the queue. Then we look at what? 6. 6 adds what to the fringe? 7. So 6 goes in. We finally find this path here. We still need to clean out the queue, so we look at 8. 8 doesn't have anything to add. 7 doesn't have anything to add. And at the very end, we have this list connecting all of these nodes back to 0 using the fastest path. Are these the fastest paths? Is it true that all of these are connected in the fastest way possible? There's no faster path? Yeah. Why is that true? Yeah.
We're going over there and kind of connected to the minimum layer that we go to.
Yeah, we're connecting things one layer at a time. So each time we go through this loop, we're accessing one layer outwards, and we're building out one layer at a time. So these must be the fastest paths. Now, here's kind of how you might build this. The runtime of this is also O of V plus E. I'd recommend trying to do the math yourself to kind of show why that's true. And we use theta of V total space. Now, depending on the graph, you are going to get different runtimes. I will just quickly note here that if you try to use an adjacency matrix, you're going to get completely different runtimes, and I'd recommend you try and come up with this math yourself. But one final note I'd like to point out. Project 2B, we are going to explicitly prevent you from using the Princeton Graphs library. Yeah, kind of the reason why is we're trying to get you to build that graph yourself. Hint, that might be useful for you. You may not need it. It depends on your exact structure. But we kind of do want you to build this on your own for this first time. You can choose different structures depending on how you want to build things. You might find an adjacency matrix work well. Who knows? It's up to you. Yeah. Here's our summary.
Well, I had a question about Project 2D.
Yeah.
I could be remembering wrong because I did it like a week or something ago, and I forgot about it because the grade system wasn't up. So I'm just looking back at it now. But when I submitted it to grade stuff, one of the auto grader tests I thought was kind of weird. One of it was one where it was like a k equals 3 case, and the expected value was